And we're off. So chapter 13 was all about the idea of I don't know the real answer, so how can I get a somewhat good estimate of it, right? That's what we're talking about. And we learned about percentiles. Let me just go over all the things we talked about so that we can practice it today. Percentiles, quartiles. The age-old question that we've noticed in this class a whole lot is like, hey, we have something we want to know about our population, like all U.S. voters or something, or all Fresno County residents or something, Fresno and Madera County maybe. And we'd like to know something about all of them, like who are they going to vote for? What's the percentage of people that are going to vote for candidate A? But we can't interview all of them. We can't get all of their information, and so we just have to take a sample, and if it's a good sample, a nice random sample, right, then we can make some inferences about that population, and usually it's decently accurate. But you know, and I know well enough now, you've read about it enough, that if you took a different random sample, you get a different answer for your percentage of people in that sample who are going to vote for this candidate, right? You're going to get a different answer, and so who in the world knows what the real value is for the population? How can you infer properly? Because it's never going to be the right number. It's not going to be exact. But the idea is that it's going to be close. And so if we could have a bunch of samples and kind of average together all those different samples percentages for candidate A, then you get a really, really good estimate, right? And that was the topic that we talked about. We talked about bootstrap sampling. How can I get another sample without having to go out and ask people more things? That was what bootstrap sampling was all about. If you sample from your sample, in theory, you will get a bunch of other samples, because if you sample with replacement, you'll get a bunch more samples that look somewhat similar to your original one. Somewhat similar, yet different, because you're going to clone people and delete other people. And so you got all these different bootstrap samples that are also indicative of your population. And maybe they're more indicative. That's the goal. That's what bootstrap sampling was all about. And the idea was that if you had a good first sample, then you're good. That sample probably reflected your population. And so all of your bootstrap samples, your samples from your samples, or your resamples, those are going to also look a whole lot like your population, but maybe in different ways that your original sample didn't really think about, which is good, because then you have more options and more values that kind of fluctuate, and that fluctuation is kind of what you wanted to know in the first place, because you can never estimate exactly what your population's your population's parameter was. But if you take enough statistics from your samples, then you can get pretty close, and our goal with this was to get to confidence intervals, right? Our confidence intervals. The idea was that we took a bunch of different bootstrap samples, or we took a bunch of different samples if we were able to actually do that, but we're doing it with bootstrapping. And we got a bunch of different values for our estimate of like candidate A's percentage of who's going to vote for them. And with all of these estimates, because we know that our answer is never going to be exact, we can take different percentiles. That's the whole reason we learned about percentiles. We can take the 5th percentile and the 95th percentile. That's kind of in the middle. There's 90% of our estimates, and that's called the confidence interval. Now we can say that, okay, here's the data that we generated that we think is indicative of our population. If we are estimating that 90% of the time we're going to be right if the number is between here and here. And that's an estimate. That's a confidence interval. We can say if we were to do this again, we are 90% confident. You can say it's 95% confident if you move these around, right? Move these that way. We are something percent confident that our true parameter for our actual population lies within this range, and this bootstrap method gives us a range. It gave us that range in between places. So let's look at how we did this in code real quick, because today is just all about playing around with that. Let's see here. Maybe we should do the very first one. Yeah, so we had, it was San Francisco, right? It was San Francisco and people working for the city. We pretended that we interviewed only 400 people in the city. We had the actual true like median value for how much money they made, but let's pretend we didn't. We pretended that we didn't, just to prove that all this works. Like, here's our sample. We interviewed only 400 people rather than the 30,000 who worked for the city. And we were able to notice with bootstrap sampling, like we got a range, a confidence interval, that did have the correct true value for median population and also average population. Average salary and median salary. compensation. So yeah, that's what happened. And this is just one sample, but if we kept sampling from our sample, that's what we did again here, it kind of looks the same. It kind of looks the same, but it's slightly different because we've cloned people, deleted other people. That's what bootstrapping is all about. You sample with replacement, or you can just say sample.sample. Remember that. So you can go to this code. I'm going to have you use some of it today, of course. And we can just keep on doing that. Take our sample, sample from it. We did that a bunch of times, right? Sample from it. And then we have another value for whatever statistic we care about, which in this case was median salary. And we did that. Like, all right, resample from our sample, get the median value there, and just do that a bunch of times. And now you've got a range then of medians. You've got a range of all these values that we cared about. And all these different resamples gave us different values. And the red dot was our actual true value because we were able to actually know the true value because we had the data on everybody, but we pretended that we didn't, just to show that bootstrapping works. And you can make a confidence interval out of all these things that we've generated, out of all these different simulated samples, kind of. We did a 95% confidence interval. So we went from the 2.5th percentile to the 97.5th percentile. In the middle of that is the middle 95% of your data. And these are edges, right? These are ends. And it's saying that, all right, 95% of the time, the true value is going to lie between this and this for the median compensation. It's a decently wide interval, but that's as good as we could do. That's as good as we could do for that sample size. And that's the whole point. That's the idea. And the actual value really was. It was, where was that? It was 135-ish, 136-ish. That is definitely within this range. And so even if we didn't know the true value, we usually never do, we can be pretty confident that it is within that range, and it really was in this case. And we're proving to ourselves that it really does work. Okay, so that is bootstrapping. That is confidence intervals in a nutshell. Do we remember? Are there any questions about that? I'm sure we read about it by now. So yeah, with a bunch of different angles, I want to try it because the goal for today is just to practice, because this is really something very easy for me to ask you to do on a test, right, on our final. So I really want you to try it. Let's get the Titanic involved today, and let's prove that bootstrapping works even for Titanic passengers. So let's pretend that we don't have all the data on everybody from the Titanic. Let's pretend like we're only interviewing the people who got onto this lifeboat or something, and all the people who they remember, something like that. Let's say that we only had 100 people, like this was right after the accident or something. We only have 100 people, size 100 sample. Let's see what we can glean from that 100 sample about everybody who was on the Titanic. So that's the goal of all this, right? You have a sample, you want to infer something about the population. So let me include the Titanic data set, and we'll talk about it in just a second. But I want you to try this too. We've got plenty of time today. Data, titanic.csv. And so here is, oh, sorry. I have to include all these things. I gotta import my stuff, and then it will work. So what I want us to do, and I'll give you some hints as to how to do it, and then I'll give you fewer and fewer hints on the next examples. But I want us to use bootstrap sampling, and I'd like us to make a 95% confidence interval for the average age of passengers on the Titanic. All right, let's pretend we only had a size 100 sample of passengers, so we're gonna have to get that first, and then we'll talk about like how to do all these things. I'll go through it slowly, and I want you to try to do it too, and you'll ask questions. All right, so let's see. The first step is we have the Titanic table. What we want to do is get a sample of this table. Pretend we're only like interviewing the people who got onto this lifeboat or something. Pretend it was a random sample. And we want their average age. And unfortunately, some of these people on the Titanic, we don't know their age. This NaN means not a number. It's just the default value that means we didn't have data on that person. So we had no clue how old Mr. James Moran was, and I'm sure that's true for many other people on the Titanic. So in order to get a sample of people with actual ages, we're going to have to exclude these NaNs. And so here's one way to do that. So I'll say like Titanic, let's do a dot where on age, and let's get it where the values for age are above or equal to 0. because like any real number, it's like anybody's real age is above or equal to 0. This nan is going to get like squashed away if we try that, and so that person got excluded. This will give you everybody who actually had an age on the Titanic, and so maybe I can call this Titanic 2 or something. All right, so here then I have a table called Titanic 2 with everybody with a real age. So that took away a few people, but that's probably as good as we can do anyway. So yeah, what I'd like you to do, we'll do this slowly together. Let's pretend that this was right after the accident, and we didn't have the data on everybody, but we wanted to infer the average age of passengers. So the very first thing we do is we got to interview 100 passengers, and so let's get them. Let's get a size 100 sample of Titanic passengers, and we don't want to clone anybody right now. We just want the actual passengers, right? Who are you? What was your age? And so this is going to be sampling without replacement, right? Do not put them back in so that they might be drawn again. Don't clone people. So try to get a size 100 sample, and then we're going to try to bootstrap as well. All right, so I've got Titanic 2 here. Let me give you all of this code, all these new things, which was just me including the table, but I'll give that to you too once this loads. I'll try to include and get all this stuff. So let's see, plus. Good. So if you refresh our chapter 13 file, you should have everything that I've typed in so far now. And so our first step is let's interview 100 Titanic passengers. So you're going to sample without replacement. All right, so take a size 100 sample without replacement. And then kind of what we want to do is we want to get the average age using bootstrap sampling. And so we should probably, like we did before, let's make a function that just does that really quickly for us. So after you got your normal sample, maybe try to make a function to generate a resample. It's a sample from the sample. Resample from your original sample and give back the average age of that new resampled thing. And this one, with bootstrapping, it's with replacement. All right. So these are your two tasks right now. Are there any questions about how you might do it? Because that's the start of it. We're going to prove to ourselves that bootstrapping works. So we're going to set up the scaffolding right now. Let's pretend we only had 100 people. Go get 100 people. Your 100 will be different from my 100. Random. Unless whatever. Once you feel enough to say, not get the same sample. Very hard to do. But try to get that, and then try to make a function that gives back what we care about after doing the bootstrap. Resync them from our sample. We're caring about average age right now. So go and get the same number of people, but sample with replacement this time. And see what the average age was of those people. And you can use this Titanic 2 table where there's actual ages. And so you can just get the average age, just go to this column and get the average. Does the process make sense? Give that a try. I'll give you a few minutes. Let me know if you have questions. I'll help you. Because it's better for you to get it before I show you.
Which table is it?
Oh, this will be the Titanic table.
Okay.
Yeah, you can go to the code for class in the chapter 13 file. You can see me importing it because we do have to do something with their ages.
Yeah.
Make sure there's no nans in the age.
Okay.
Have any trouble? What is this? Oh, nice. Oh, wait. No, I did that wrong. Should be able to check that your function, if you run it a few times, it should give back different values, right? Different values. See, that's actually doing something new. Resampling from the sample with replacement. And that gives you a different looking sample. I can do that later. All right. All right. I think that's about my timer. Are there any questions? Let me do the first part at least. So I want a sample of the Titanic people. Just we're pretending that we're only talking to 100 of them, rather than like the 800-ish original. I guess 700 people with ages. So I'm gonna say Titanic 2 was the name of the table that I gave it, where I got rid of all the ages that didn't like have ages really. So that's Titanic 2, and I'm gonna take from that a sample. Say dot sample, and for sample, you can always ask like, hey, if you don't want to go to the documentation page, you can always be like question mark, and it will tell you more about that function, that operation. It's like, all right, to sample, you say how much you want with replacement. By default, it's true. There's also something called weights, which I have not taught you. And you can read about that if that ever matters one day. You might need it. So it's kind of nice. So I want to sample 100 passengers, please. And I really do not want replacement this time. I want like separate passengers. Don't clone anybody, please. This is like I'm interviewing real people. And people aren't clones of each other, unless they're twins or something. So I'll say false, and that will give me a sample of 100 passengers. This is my random 100 passengers where nobody's been duplicated, and I'll call that sample like I've been. But you can call this anything. Just be like, all right, passengers. Call it whatever you want, but I'll just call it sample. And now that's what I've got. And then from that, I want to a million times maybe get a resample from the sample. It's always this image in the back of our minds, right? It's always, all right, here's my sample. I want to bootstrap it. I want to take resamples from it. I want to resample from it, I guess is the verb. Give me a sample that kind of looks like it, but I've cloned people now. I'm getting a different looking thing because maybe that clone person is more indicative of the population. And that's good because that gives me something different looking. And that's like another sample. So that's my resample. So let's do this just outside of everything, and then I'll turn it into a function. How about that? But are there any questions before I do that? So that we've got the 100 people. I've called them sample. So all right, give me, take my sample and sample from it. Just as many people with replacement equals true this time. This will give me, because I called it sample, it's kind of silly. I could have called it like S. And then it would have been like S dot sample, but I call it sample. But like sample dot sample from my sample, right? Sample from my sample, just as many people with replacement this time so that I clone them and I do get a bootstrap sample. I get a resample where maybe that younger person was supposed to be cloned. Maybe I didn't have enough young people in my original sample, and that's good. It's taking care of that if I do this enough times. So the default is with replacement, so I can get rid of this. And the default size for your sample is the same size as you had. Like they made this library with the idea that you're going to do bootstrapping. So I can just say sample.sample. It's happy. And I can call that's my resample. Boop. And my goal is to go into that resample, because it looks like this again, right? It's just got clone and deleted people. I'll go to the age column of that and get the average age, because that's what we care about right now. That's what we're pretending to care about for this example, right? We want average passenger age. So, all right, that's the statistic I care about. So go into the age column for this resample thing and give me the average. Something like that. It's like that. That's the final answer for my resample thing. And every time I run this, I get a different value because I'm taking different, like, I've got a different group of people, right? I've cloned some people, I've deleted some people from my original sample. That's the goal. And so I want to do this a bunch of different times because that's giving me another window into the population, even though I only had 100 people really. Okay? So let's turn this into a function now. So def, give me one bootstrapped average. That's kind of how your book likes to call it. Give me one of this kind of thing. It's a bootstrap process, and it's an average that I'm calculating. And so I need to return back this answer. Okay? And that gives me a function that I can call a bunch of times. One bootstrap average. A bunch of different times, I get another population, or another sample, right? Another sample from my samples, as if I went out and interviewed more people. And I'm getting different values for the average age of this new group of passengers. Sometimes it's older, sometimes it's younger. Okay? So are there any questions about this bit? We got the sample, the original sample, like we interviewed people, we're pretending. And then from that, we're generating more samples with the bootstrap process. We're resampling. So give me a sample from my sample with just as many people, that's the default, and with replacement, that's also the default, so that people get cloned. And that's going to average away, if I do this enough times, any of the issues with my original sample, which is nice. So what I want from my sample each time is I want to know the age, and I know that if I took new samples, I get different values for ages, and so this is simulating that process. So here, go and give me the age column, give me the mean of that. That's the statistic I care about. And this will fluctuate, and how much it fluctuates will tell me where the true value might lie. Okay? That's where we're going. That's what we're doing. Does this part make sense to us before we move on? Questions about that? Because now we want to do this a bunch of times, right? So using bootstrapping, right, we're going to try to make a 95% confidence interval for the average passenger age. That's this kind of thing where we cut it off on the ends with the percentile function. And we have some examples of that in this file above from last time. But yeah, the idea is, well, we got to pick a number. How many times we're going to call one bootstrap average and keep track of all these things? So let's say 5,000 times. Let's say generate averages from 5,000 bootstrap samples. Okay. So what I'd like you to do now is, it's very similar to things above. If you scroll up, there's a lot of things that are very normal and things that we kept doing a bunch of times. I want you to follow that lead and try to get an array of a bunch of different bootstrap averages. So you're going to call this function essentially 5,000 times, right? And get a bunch of different averages and see what you find. Okay? So try to do that. And after that, we're going to get a 95% confidence interval for that average age. So I'll put that in another cell if you want to try that too. 95% confidence interval for the average age of those passengers. And this is nice because it helps us prove to ourselves that this is the right thing to do. This will actually work out because we do have the average age of everybody on the Titanic. We're not looking at that yet. We're only using and considering our sample. If it was a good sample like ours was, just like we're forced to have a good sample here because it's perfectly random and without replacement. That's as good as you can do in real life. So this is going to show us that if you got a good sample, you can infer things about the real true population. Because usually you don't have that number, but we have it now just for educational purposes to see that it really does work. I'm going to have to listen to whatever that means. 5,000 of those guys. That's really cool. Okay. Well, let's do the 5,000. And then we can talk about the other thing if you're still working on it. Are there any questions before I show you like the 5,000 bootstrap samples? Because we're just calling that function a bunch of times and keeping track of it, right? By appending to an array that we make. So I like to give a number. It's kind of what your book likes to do. So I'll get you to practice that. How many times are we doing something? 5,000 times. And it's easy because we can go to one spot and change it. We can see what's happening with the variable name, but we didn't have to say that. We could have just hard-coded the 5,000. And what am I doing? I'm getting 5,000 bootstrap samples. I'm taking averages. So you can call your array whatever you want, but we need an empty array. And what are we going to call this array? Call it whatever you like. I'll call it bootstrap means. So these are my bootstrapped mean values for the average age. And so I want a loop for I in np.arange, my num repetitions. What do I want to do? I want to call one bootstrap average a bunch of times, append it to my bstrap means array, and then call that bstrap means again. Have it get bigger. So we got all those guys, and if I run this, it'll take a little bit, but I will get my 5,000 bootstrap average values. Not too bad, right? And then I've got this big long array of size 5,000, and it's got all these values in it. And the idea is, if I do a histogram real quick, oh, sorry, I got to turn it into a table, don't I? Table with column means, bootstrap means, histogram. There it is. Got all these values, and I want to get a 95% confidence interval. Like cut it off. Like I can be 95% confident the values between here and be 100% confident-ish if you just use the whole range. But usually you kind of say 95 because that's a good enough value that people like to care about, right? So we want a 95% confidence interval for this average age. How will we do it? With the percentile function, right? So if you haven't tried that yet, go scroll up, look at the way that we did that before, but try to figure out what are the ways that it's going to cut this off, these values, this bstrap means table, not table, but array. How you cut it off with 95% in the middle. What are the values that you give to percentile? Because you're going to call percentile twice, aren't you? This is amazing. See it? So if you want 95 in the middle, you're going to cut it off at like with 2.5 and 97.5, right? That's the range with 95% perfectly in the middle. Okay? Let's see here. Where was I? I want to be on this file. So how do we call it? It's going to be percentile. And you give the percentile in an actual percentage form. It's 2.5. It's not 0.025 or anything like that. It's like legitimately give the percentage. And then bootstrap means is the array. And that's going to be the left half, right? And then we call it again. 97.5. Give me the 97.5th percentile value from this array. And I guess I've still got it showing the thing, but here's the output, right? Between here and here, we are 95% confident. And if we did this again, the true value would be within here for the actual population. And we can actually compare, right? Because we do have the actual population. We have the true entire Titanic data set with all the people's ages. I call it Titanic 2 with actual ages. So let's just go to that one. What's the average age of the people that were actually on the Titanic that we remember the ages for? Average age was a little less than 30. And is that within our range? Absolutely. So that's going to show that this process really does work. Even if you have just one sample, if it was a good sample, it reflects your population well. And so your statistics based on that sample, if you do enough of them with different if you bootstrap, then you're going to get this range. And though it may be wide, depending on how big your sample is, it usually, if you do a 95% confidence interval, 95% of the time it will have the true value in it. That's how you can think of it. Okay? And it really did. That was the true value. And here's as kind of as good as you can do with a sample. You can get a range. But you can be pretty confident. We're showing ourselves that we can be confident that that value lies within that range if it's a large confidence interval. 95, 90. Once you get smaller, it's like if you do a 50% confidence interval or something, then there's only a coin flip chance that it's within that range. But it's still, that's a useful thing to care about. Okay? And so yeah, that is a 95% confidence interval for average passenger age, and we calculated that from an original size 100 sample by bootstrapping. Does this process make sense to us? Are there any questions about it? Is it coming back? Because that's it. That's what we want to keep doing. That's how we practice. So let me give you all this code, because we're not done with Titanic yet. So now you should have all the code that we've done so far, including all of this. I want you to try to do the same thing, but I'm going to give you less instructions. So let's go back to the original Titanic table. And we definitely, even though we don't know people's ages, we definitely know whether they survived or not. That one was easier to come about. So we have the survived column. It's always 1 or 0. 0 if they didn't survive, 1 if they did survive. What I'd like you to try to do is, again, take a sample. You can use the same one if you want, but that's fine. Try to do a 99% confidence interval for the survival rate. All right. Again, with a size 100 sample, try to get a 99% confidence interval for the survival rate of the passengers. Construct a 99% confidence interval. You can use the original Titanic table for this. Confidence interval, but you got to take a sample just to prove to yourself that only if you had like a few people that you interviewed, you can still get a good answer if you took a good random sample. Interval for the survival rate for a size 100 sample. And this is kind of useful, right? If you're on a lifeboat or something, like you only had the people on that lifeboat to talk about, and you can ask them like, all right, who's there? Who do you remember wasn't making it on the lifeboat? Like you can get a decent answer if you didn't have all the information, and that's what data scientists do. That is exciting, though this is a bit of a morbid example. So yeah, try to get a 99% confidence interval for the survival rate for a size 100 sample. And one way to get the rate of survival is just like get the average of the survived column for your sample. So try this. Again, using bootstrapping, you can do 5,000 again. You can copy and paste a lot of things, but what we're asking for changes. So try to think about what you need to do different. Any questions about the question? So I just want us to practice today. This is a good thing to know how to do. We only interviewed 100 people, so go get those 100 people. So we have to move with a sample without replacement. and then we want to do like 5,000 bootstrap samples. So it's a good idea, again, to make a function, just kind of do the whole process all over again. That samples from our sample get a resample. And from that, what do we care about? This time it's survival rate. So get the survival rate for your resample. Make a function that kind of gives that back to you. So you can call it 5,000 times, or however many you chose. And then you got your array of all those different values, and they're going to fluctuate because you're sampling with replacement for your resamples. That'll look more like the population, some on average. And then you want a 99% confidence interval over the values that you got back after you did those bootstrap samples, after you got those survival rates for your resampled samples. So you have to think about what are the edges? What do I use when I call percentile to get a 99% confidence interval? How can I put 99% of those things in the middle? Maybe a few minutes to try this entire process. Let me know if you have questions and I can help. I'd rather help you than show you the answer myself. It wouldn't be a rate if it was just the sum, just the number. So after that, but if you divide it by 100, then it's something rate. You could do it in a bunch of different ways. So yeah, one way to do it is you sum them all up and you divide by how many. That's a rate. It was a 1 they survived. Or you can just take the average of the ones and zeros. Either way works. Because that is the average at that point. Yeah. Mm-hmm. Another minute or so, and then I'll show you my answer.
Do you have to construct a table of this as well?
Yeah, you do the whole thing. You don't have to make a table if you don't want to do a histogram. Like, you don't need a histogram to do all of this. That would be the only reason to make the table. You can just keep it as the array, because all you need when you're calling percentile. is to get an array. Now we'll prove to ourselves that this works. All right, let's see. I will take another sample. Again, I will call it sample. All right, let me make a new column here, new cell here. So sample is, we've got, take the original table this time because everybody has survival data on them. I'll sample 100 values and I'll say with replacement equals false because I don't want to duplicate anybody. And I want survival rate. So I kind of want to do this. I want to take a sample from my sample and get back the average survived value, right? Because that'll give me the survival rate if it's just a bunch of ones and zeros. So let's make a function that does that real quick for me. Give me back one bootstrap. That's what we tend to call it. I want a rate this time, not an average. I guess it is also an average, but that's fine. One bootstrap survival rate, please. And so again, you can copy and paste a lot of stuff, but I'll try to explain all over again. We would like take our sample, give me a bootstrap sample with just as many people with replacement this time. Those are the defaults. So sample.sample will work just fine. That's my resample. I've sampled again, and then I would like to, from that resample, give me the survived column, and take the average. I could say .mean again. We did that last time. There's a bunch of different ways to get the average. It would be like np.average on this, right? You got a million different options, and then I want to return that. That will be the process, right? One bootstrap, let's call it rate for this one. If I call this a bunch of different times, there's survival rates of that sample. Sometimes they look to be similar a lot of the time. Interesting. Sometimes they're different. But again, now, a few thousand times, let's do this. Let's get a bunch of bootstrap rate values. 5,000 is a good amount. I'll call this bootstrap rates. One bootstrap. Let's call it one bootstrap rate here. I hope I changed all this properly. Yeah, so now if I run this, I've got a big long array. It's going to take a second. And all these different values for my resamples of the statistic I care about for the survival rate is in this bootstrap rates array. A bunch of different values. And if I want a 99% confidence interval, I need to cut this off with 99% smack dab in the middle. So if you think about that long enough, you're going to notice that, okay, it's percentile. It's between the 0.5 percentile and the 99.5 percentile, right? 99, how do you say that? 99.5? I honestly don't know if that's correct English. Bootstrap rates. But those are the things. You give those. And so it's like, all right, with 99% confidence, if I were to take another sample, if I were to look at the, take another sample and get the population, like if I were to do this process all over again, 99% of the time, it would work out that the true value for the survival rate of everybody on that Titanic is within this range. We took a good sample. This will be correct 99% of the time. And we have the luxury of knowing everybody on the Titanic. We just took a sample to prove to ourselves that this works. We're just pretending we only interviewed 100 people on a lifeboat or something. But if we look at the original Titanic now, Titanic dot, I guess I can do this. It really was just from this column, not resample.column, but Titanic.column survived. The average, the survival rate on the actual Titanic was 38-ish%. And that is within this range. It's a very wide range because we wanted a very accurate answer. If we wanted a 95% confidence interval, this range would be a bit smaller. It's going to widen when you want more confidence, of course. But the true value really is within here, which is proving to ourselves, showing us that this process really does work. You had a good first sample. These resamples are going to average away any potential issues, and it will give you a range when you make a confidence interval that tends to include the correct value if that confidence interval was a big one, which is awesome. Any questions about that? See the process working? So yeah, my suggestion is try to do a 95% confidence interval, 90% confidence interval. It's hard to say for this, and watch the values change. Watch the range change. The range will get tighter if you have a smaller confidence interval. Try to change the width of the confidence interval, but also the sample size as well. Like if you had a size 200 sample of people on the Titanic, then there's less wiggle room, which is interesting to think about. So also in addition to that, the sample size as well. So try to change that as well. Sample size, and see how the width of the interval changes. It's kind of nice. It's something that we talked about before. So yeah, that's a good example. Are we ready for the next one to try? That's Titanic. We've done enough Titanic for the day. I got two more I want to try with this. Let's do the fish diet one. So this is the men on how much fish that they ate and whether or not they got prostate cancer. So let's do the same thing. We're going to play the same game. We're going to pretend we only had 100 people. And again, I just want us to play around, get this process in our minds so that we'll never forget. So let's read in that table. Fish diet, .csv, and I'll call that diet. And so here is our fish diet table. Oh, I forgot to end. There we go. So here's the table. It's in an order, so if I do like a quick little sample of the table, you can quickly see the different values that you get. Like here are the different amounts of fish that people ate, and the cancer value is either no or yes. If I do another sample, sometimes there's a yes. There we go. So they're all there. Our goal, and I'll let you do this one pretty quickly, is let's again pretend instead of 6-ish thousand people that we only had 100 again. We're interviewing 100 people in Sweden, 100 Swedish men, and asking how much fish that they ate and following along with their lives and seeing if they ever got cancer. Let's again pretend we only had 100 people. All right. And what I'd like you to try is to calculate a 90% confidence interval for the total cancer rate. So just like everybody, whether or not they got cancer, total cancer rate, just like survival rate that we did for Titanic. So you don't even have to look at this diet value. Look at the cancer column only. Try to get the total cancer rate among like Swedish men in general. So here's the process. So take a size 100 sample, construct a 90% confidence interval. So think about where the edges of that are going to need to be for the total cancer rate, just of everybody. You don't have to even look at the diet column. And then so among all the kinds of fish diets taken together. So you can ignore the diet column. All right. That is ignoring the diet column. You don't care what kinds of amounts of fish that they ate. Just want to know if they got cancer or not. So yeah, the way that you can figure out the total cancer rate for everybody, because we're going to try to estimate this, right? The total cancer rate for everybody was you take the whole thing, diet.column, give me the cancer column, and that will give you the yeses and the nos. And what you can do is you can compare that to, was it yes or not? Was the cancer value equal to yes? Now you got a bunch of trues and falses. And remember that as far as Python is concerned, true is 1, false is 0. So now it's just like survival. And you can take the average of this, which is weird, but you can say np.average. This was the total cancer rate for everybody in the study. And so we're going to try to estimate that by taking a size 100 sample, pretend we only had 100 people, and get a 90% confidence interval of the total cancer rate using this kind of way of doing that for getting the cancer rate of a table. You're going to make a sample though. So try to do this. And in your 90% confidence interval, 90% of the time, you're going to get this value. This was the true value. We're pretending we didn't know what that true value was again. We're just proving to ourselves that this works out because we never have the real answer in real life. We're proving to ourselves that this process really does do the right thing when we know the real answer. Then you'll feel empowered to do it in real life, even though you're not sure. So yeah, same process all over again. Get 100 Swedish men sample without replacement, so that you have 100 distinct Swedish men. Even though they were actually twins in this study, which is fine. Don't worry about that later. Get your Swedish men, get a function going that gives 3 samples from your sample, finding the cancer rate of all those people. And if you do this enough times and your sample was good enough at the start, and it will be, because there's no way to get a bad non-random sample out of Python in this way. You had a good sample. Resampling from it then will give you a picture of the true population, which is very useful. Try to get a 90% confidence interval. I almost guarantee this value will be within. That's the true value. I'm gonna give you like a 2-minute head start. Where did that come from? Just to keep time. It's so loud. That's okay. Here we go. Let's try this. So, okay, I assume you're getting used to the process now, but I want to just keep on explaining it, because I know the more I say it, the more it's going to sink in. So, let's do it. I would like to interview just 100 of these Swedish men. I want to sample from this original table, pretending we only had that many people to work with and no more. So I'll say diet.sample. Give me just 100 of these people with replacement equals false. Don't clone anybody. And I'll call that S instead of sample this time. It doesn't have to be called sample. Call it whatever you want. And then I'm getting cancer rates for these people. So I'm going to say def1 bootstrap. It's rate again, right? And how do I get a rate? I want to take a resample. So take my original table, sample from it just as many people with replacement. Those are the defaults. That's a new resampled table. And what I want to do with that is get the cancer rate for that resampled table. So hey, go into the resampled table. It looks a little bit different, but it's modeling the real world as good as it can if I do this enough times. It's like I got another sample. So I want to return this value. Return whatever I get back from this. All right, and that's my process. And I want to do this a few thousand times. Again, we can do it 5,000 times. Sure, that's this process, right? So 5,000 times. Hey, call it bootstrap rates again. That's fine. Yeah, I gave the same name. That's perfect. So all this code works still. And then if I want, I'll do this all in one cell. Then if I want a this original one was a 99% confidence interval. If I want just a 90% confidence interval, what are my edges? What's going to be on the left side if it's 90% confidence interval? So I want 90 in the very middle. What are our thoughts? There's not 0 and 90, right? Because that would be like to the left. Do you see what it has to be? I want a 90% confidence interval. I want 90% right in the middle there. That's what I want.
5 and 5.
Yeah, and 5 and something. Like 0 and 90 is like this left side. It's been squished on the left. We don't like that. But if you start at 5 and you go 90%, where does that end you? If this is 90% wide, 5 plus 90 is 95. See that? So the 90 is in the middle now. It's smack in the middle. That's perfect. Does that make sense to us? So that's what we need. That'll give me a 90% confidence interval, so that's going to be 5 and 95. Cool. And this is one big long cell. It's going to take a while, or not. I guess the data set was decently small. So this is my, these are my values. And it looks like with a 90% confidence interval, we got this range. We just happened to. We'll get a different range if I run this again, of course. But do you see how the true value, even though it is on the edge, kind of, it is within it. So it is showing us that this process works. 90% confidence interval is right 90% of the time. If I do this again, I'm going to get a different interval because I'm going to have a different sample. And this one, I am within the 10%. Sometimes it's not right. Sometimes you don't have the true value. Maybe if I widened the range, like then it would have worked out. But 1 in 10 times I'm wrong here. But this time I'm right again. So that's kind of nice. Yeah, that's what goes to show. So are there any questions about that process? Is it sinking in? I hope you see how useful this is, right? You don't know the true value, but you can get a range. You can get a range, and that's as good as it gets, really. It's really nice. So, question, yeah?
So I keep doing it over and over, and I'm constantly getting the same number for both.
It's
and it's the exact same one every time we run it. Like,
yeah.
don't know where it's from.
Let me take a look real quick. If I can't see it quickly, I'll come to you after class. You're taking a sample. You're returning the value. 5 to 95. And every time you're running the same values. Looks like you're getting the same value each time. Oh, it's going to be the resample. You want to take the average cancel rate from that, not the original. Resample.
Oh, you sampled that phone?
Yep, that's the table you're working with. You're just getting the same rate. That was the original rate. That was the true rate. And there it is. Yeah. Cool. Any other questions? I just have one more sample table. I want to do Pokemon, of course, as one last example. But I hope you can kind of see the power of all this. So here we go. One more example, and then that'll be it. I'll release an assignment, and that'll be it. So let's do the Pokemon table for fun. Just practice one more time, and that'll be all I got. So today is just a day of practicing, because this is a really, really useful thing. So let's get the Pokemon table. So there it is. Here's all my Pokemon. I'll have to get a new table eventually because they're making more, aren't they? But I got all this data on all these different Pokemon in the Pokemon world. And let's one last time play this game. All right, you know what to do. You know the process. So let's pretend you've only got take a sample of only 150 of the Pokemon. We're not sure. Uh, Maybe they may not be representative. We'll find out. But take a size 150 sample, instead of 100 for once, of the Pokemon in this table. Just pretending you're only interviewing 150 of them. That's all you got. And try to use the bootstrap process one more time to make a 95% confidence interval for the median HP value. HP is short for hit points. It's how strong the Pokemon is. How much of a beating can it take, kind of. So where is that value? I think it's just lowercase HP. There it is. So you just go to the HP column, and these numbers, it's higher if the Pokemon's like stronger. It can take more damage. So go and try to get a 95% confidence interval from a size 150 sample. So not everybody. Again, pretend we didn't have everybody. We'll compare and see like if this is actually a thing that is useful. It's not necessarily the case that 150 Pokemon are representative of every one of them, because they do change them around every season, but we'll find out. So pretend you only had 150 Pokemon to work with, get that many of them as a random sample without replacement so that you don't clone anybody, and then using the bootstrap process, which does clone people because you're getting new samples from your original sample, make a 95% confidence interval for the median HP value. So it's not average HP, it's the median HP. And so there is np.median to get medians. There's also, you can use the percentile function to get a median as well, right? That will be the 50th percentile is the median. So yeah, some options, but try to do that. I'll give you a few minutes and then I'll show you my answer. It's going to be very similar to all the stuff that we've done. I think we did do median as maybe our first example. If you scroll way up in this file. But give that a try, I'll give you a few minutes, and then I'll show you my answer, and then I'll wrap up. Please let me know if you have questions. I'll be happy to help.
Is it with replacement or without replacement?
For which part? It depends on what we're talking about. If you're taking the original 150 sample,
Yeah.
then that's without replacement. You don't want to clone any Pokemon. Just like you don't want to clone any of the Titanic people. It's like we're going out on the street, we're going to be interviewing 150 separate Pokemon. So that's without replacement. But bootstrapping, that's for sure with replacement. Then you do want to clone people, because maybe that was useful. Things will look different if we do that. Another minute, and I'll show you my answer. Any questions before I show you? Let's figure this out together. So I should be able to do a lot of what we did. I will steal most of this. We'll call it sample again, but it's from Pokemon. The table's name is Pokemon. And I want 150 Pokemon without replacement, because I want separate Pokemon. It's like we're interviewing 150 separate people, but I guess you can have duplicate Pokemon in the world, but that doesn't matter right now. Size 150 sample. It's like we're interviewing 150 separate people. Like that was we went out and we did that. And then what I want to do is get median HP values using the bootstrap method. So assuming that I only had those 150 people, 150 Pokemon, that was my one good sample. Let's sample from it. Let's resample from it. So sample.sample. And get back a median HP value. So one bootstrap, I guess median probably is the right way to call this. Median. And so from this value, I want the median HP. That's what I want to do for all of these resamples, to get a different value, see how it fluctuates. So that's kind of the point. So go into the resample table. It's got different values. It's got different Pokemon. Some have been cloned, some have been not cloned, some have been deleted. Maybe that's more indicative of the population. If we do this enough times, it kind of averages away any issues. That's the goal, at least, of bootstrapping. So go to the HP column and get the median value. That's what I care about. np.median is one way to do it. Percentile, to get the 50th percentile is another way to do it. And then 5,000 is probably fine. And then it's bootstrap, let's call it bootstrap medians, right? Bootstrap median values. Medians, one bootstrap median. Did I change all the names properly? I think so. And then we're going to take our percentile, we're going to call this, these are bootstrap medians, that's our array. And, well, if I want a 95% confidence interval, we've done that one before, you want 95 in the very middle. So that'll be from 2.5, the 2.5th percentile, to the 97.5th percentile. If you subtract the two, you got 95 total, and it's right centered in the middle, if you think about it. Okay, so we're in this. It does take a second to do all that resampling. It's 5,000 times. It does take a bit of work in the computer, but eventually we will get back a range that we can say with 95% confidence, we can say 95% of the time, this range that we're about to get holds the true population for every Pokemon ever, their median HP values. Let's figure that out. I guess while it's trying that, how do you calculate the true value? Again, we're using all these, so 62 to 70, that's its guess. That's what it thinks. All right, with 95% confidence, or 95% confidence that the true median HP for Pokemon between 62 and 70, which is not the world's largest range, which is nice. So that's kind of cool. And then we can compare, because like usually this is where you stop as a data scientist. Like that, this is the value, this is the range. We only have the sample, that's all we know. We don't know the true value for the population. We're trying to estimate that. Here is our estimation. It's a decently small range, which is nice. But we can, just for this chapter, I've used a bunch of data sets where we know the true values. We know the true values. So we can do that. We can say np.median for this whole thing. It's the whole Pokemon table. we do have the population data. So we can get the true parameter if we wanted to. It looks like it's 65 is the median HT value for every Pokemon. This really did work. We proved to ourselves that it did work. Usually you don't get to see that. You never have the true value. You're trying to estimate it. But we have proved to ourselves several times now, we should be confident that this process works. It really will give us the true value most of the time. 95% of the time if it's a 95% confidence interval. Does that process make sense? Any questions about it? There's one thing, did I forget to say it? One thing I do want to do before I close, one thing I forgot to say is, if you think about it, if we go back to just remember this, if you go back to the fish people, the Swedish men eating fish data set, that data set was a sample of Swedish men. Like the whole data set was a sample of Swedish men. So like, forget about 100, we could use the whole thing. So this, just by virtue of the way they made this particular data set for the study that they did, the data set itself was a sample from the population of Swedish men, right? So we can do this whole process with the whole data set, is what I'm trying to say. And this is what you would actually do as a data scientist. Like, okay, the whole data set was a sample. Let's use the whole thing to predict the average cancer rate for all Swedish men, because that was what the sample was over. So, oops, I would like a cell right there. So I can just do all this with the whole thing. Like the whole table was a sample. So I don't have to get another sample. Just take the whole diet table, resample from it. Does that make sense? Do that. It would take a long time to do 5,000 repetitions because it's a very large table. So let's do the same thing for this one. That'll take a second. So this is going to give me a 90% confidence interval. Just for fun, we can also do a, we can do a 95% confidence interval. So do you see how this is just a 90% confidence interval, first of all? This is a range. This is a 95% confidence interval. You see how it's widened? It's gone on the other ends a bit farther because like it has to be more accurate. But it hasn't widened that much because the sample size was very large. So it's saying with 90% confidence, the cancer rate, the prostate cancer rate for Swedish men, all of them, is this. That's kind of neat, right? We're not sure what the true value is because we could never know that. But it's saying it's within this range. And like if you want a 95% confidence interval, it's not much wider because we had a large sample to begin with. So not with 95% confidence, we can say that the true cancer rate for all Swedish men is within this range. And that's kind of neat. Like that was the original sample. This is what you could have done in that study. That is publishable stuff if you got that sample. That's pretty cool. So yeah, that's another nice thing. The whole data set was an actual sample of people. And like we don't know the true value, but we know it's within this. Like that's what you do as a data scientist. That's pretty cool. So yeah, I think that's a good place to leave us. Are there any questions about any of that stuff? Anything that we talked about today? We just practiced all this stuff, but kind of see the process of bootstrapping, I hope, and then how to use that to gain, to calculate a confidence interval. That's your range of where you think this value, this true parameter for your population lies. All right. If we're good, there is one assignment that depends on this chapter. It's homework 8. So let's talk about that one. Let's figure out when we're going to make that one be due. It's homework 8. Go to the calendar. Homework 8. Let's see. We've got an opening next Wednesday. Well, how about that? So homework 8, we do the 15th. Don't forget about that project. I know that'll come up, right? That'll rapidly come up. That one's a bit longer, so make sure to start working on that if you haven't already. Project 2. Remember that you can have a partner if you want. But that is when I'll have homework 8 be due. And that should do it. Yeah. I think that is all that I wanted to say about this chapter. Let me stop the recording.